Hello, a very warm good evening to all wonderful people present here. To share a token of commitment, we are back as promised last Friday with a very special speaker with us in the second lecture of this series on the solar system. This lecture series is proudly hosted by Physical Sciences Consultorium. Physical Sciences Consultorium is a consortium of experienced professionals to offer our expertise to educational institutions, industrial organizations, and newcomers to encourage innovation, build collaboration, and mitigate confusion. Science for Everyone is the co-host of this initiative and a permanent partner of Physical Sciences Consultorium in science outreach activities. Science for Everyone is a dedicated science outreach platform. It aims to become a bridge between young students and experienced professionals. It works for the popularization of science and aims to connect with people from diverse fields in a holistic approach. With this brief introduction of this initiative and hosting platform, I welcome you all this evening to join us in the quest to take a ship from cup of curiosity to explore space. The chairman of this lecture series, Professor B.M. Dixit sir, is joining us very soon. So as of now, we will be starting the program and we'll wait to join him. Currently, he's in somewhere where he can't join as of now. So in a few minutes, he will be with us. So for now, as of to continue this program, we will continue. Professor B.M. Dixit is chairman of this session, and he is professor of physics and director of Institute of Natural Sciences and Humanities at Sri Ram Swaroop Memorial University, Lucknow. And we will have him very soon with us. So as of now, to continue the program, I welcome all the participants who are with us as of now and who will later join and listen our streaming. So thank you very much for being here, and I am really excited to introduce our guest speaker for this session, and I am adding him. So very warm welcome. Dr. Manish Sanghani, he's with us, and I'm really excited to introduce him on this platform as our invited speaker for this session. So we have today Dr. Manish Sanghani to tell us about the belts in our solar system and how these belts provide us clues to better understand the process involved in formation and evolution of our solar system. Dr. Manish Naveen Chandra Sanghani obtained his bachelor's degree in physics from Kotak Science College, Saurashtra University in 2007, and master's degree in physics from Sardar Patel University, Anand, Gujarat in 2009. After that, he worked as a lecturer in physics at the School of Engineering, RK University, Rajkot, for more than 2 years. To actively engage in science education and popularization, he spent about 2 years as science educator at Vikram Ambalal Sarabhai Community Science Center, VAS CFC, Ahmedabad, and has been a part of Science Express, which is an innovative mobile science exhibition of GST managed by VAS CFC. In the end of 2013, he joined Physical Research Laboratory as project associate at Planetary Sciences Division to explore frontiers of research. He spent more than 2 years working with extraterrestrial pristine samples in NanoSense Laboratory, a unique facility fully dedicated to such studies at PRL. In May 2016, he moved to Center for Star and Planet Formation, University of Copenhagen, Denmark, for his doctoral thesis. Few months back, he was awarded Ph.D. for his work on solar systems prenatal history by a coordinated isotopic, microstructural, and chemical investigation of pre-solar silicates and oxide stardust gain. He presented his work at various national and international forums and actively participated for popularization of science. His love for science, passion for education, and vision for research makes him the best person we can get for such initiatives like ours. I have been lucky to know him as a compassionate human being who fought back against all the odds in life and supported and enriched people around. I take this opportunity to welcome Dr. Manish Sanghani at this platform. Thank you so much for accepting our invitation and giving precious time for us from your busy schedule. We really appreciate it, and in fact, we are proud to host you here. To facilitate an interaction with participants, we have a dedicated question and answer session after the lecture. The participants are requested to put their questions in comment section. The host will put the selected question to our invited speaker for discussion. With this formal introduction and announcement, I request our invited speaker, Dr. Manish Sanghani, for his presentation. Thank you. Thank you for being here. Over to you.
Thank you very much, Lalit, for giving such a nice introduction and giving me this opportunity to discuss about our solar system. I would also like to thank Professor Dixit sir for chairing the session and motivating us. He will be joining us later, as I know. And I also congratulate you, Lalit, for creating such a nice platform for the science popularization for the benefit of students and the community as a whole. So we have this third lecture in this series. So we had the first lecture, which was the overview of the solar system science by Dr. Kuljit Marhas and Dr. Ritesh Mishra sir. And we had then later we learned about the star of our solar system, which is the sun, by Dr. Vagish Misra. And my job today is to discuss about the two belts in our solar system. So I'll be discussing about the two main belts in our solar system, which is the one of them is the asteroid belt, and another one is the Kuiper belt. And these belts with their components have very large impact on the solar system studies, and they give us clues about different formation processes, formation of planets, and formation of our solar system. So we are going to discuss this in details in my talk today, in this talk today. So this is the plan of my talk. First, I'll briefly discuss about the formation of our solar system, and then I'll discuss about the asteroid and asteroid belts and its origin and different components of the belt. And now later I'll discuss about what do we learn from the asteroid belts. And then later I'll be discussing the Kuiper belt and Kuiper belt objects and the science flow for exploring the Kuiper belt objects. Then I'll switch over to the meteorites and their classification and the scientific outcomes of the study of meteorites. And later I'll introduce the pre-solar brains, which is the field of my research of interest. So this is as we all know, this is the formation of our solar system. This is the general scenario how we know about the formation of our solar system. So there is a cloud of gas and dust which collapsed by its own gravitational force and then created a proto-sun, which you can see here in this cartoon. So later on, there is a formation of the disk, and then later the disk starts to rotate, and we have in the later phases we have the planets which are come into existence. So the solar system is created from the cloud of gas and dust, and as we know, this is the general scenario of the solar system formation. And the later, so this is the cartoon which is representing the different planets in our solar system, and the sun. This is a sun, and these are different planets, four inner solar system planets and four outer solar system planets, which are the gas giants. The inner planets are the terrestrial planets, and we can see here two different belts. So one is the asteroid belt, as you can see here, and the another one is the Kuiper belt. So how these two belts come into existence, and what are the processes for their formation, that I'm going to discuss here. So the first one, which is the asteroid belt. So what is the asteroid belt? So there are millions of rocks and debris orbiting between the Mars and Jupiter, is forming the asteroid belt, which forms an asteroid belt, and it is the home to it is also the home to minor planets and dwarf planets like Sirius. And this asteroid belt is also the is this asteroid belt is also the home to minor planets and dwarf planets. And Jupiter's gravity sometimes prevent material. So how this asteroid belt came into existence in the past. So the Jupiter has a very high mass, and so the gravitational force is also very high. So Jupiter's gravity prevented the material in the asteroid belt. Uh, just a second. Yes. So Jupiter's gravity prevented the material in the asteroid belt to form or coalesce to form the larger planets, and they are like the small debris and rocks are orbiting the sun. That's why. And the asteroids are mainly made of rocks and metals, and they are irregular in shapes and sizes, and the gravitational forces sometimes throw the asteroids from the main asteroid belt and deflect them from the orbit, and sometimes they visit the Earth, which are which are the which and when these asteroids visit the Earth and comes to Earth, they are known as meteorites. So there are so as you can see here in this cartoon, in the right hand side picture, this is the cartoon of the asteroid belt. Now what we know about the asteroids and why do we study asteroids? So from the data which we have from different missions and orbiters and flybys and landers and different spacecrafts, there are mainly three different types of asteroids. One is the stony one is the stony or S type of asteroids, which is about 17%, which is made of metallic iron and nickel and iron silicates and magnesium silicates. Another one is very interesting, and it is the C type or carbonaceous type asteroids, which are of the which are the 75% of all the asteroids. We have millions of asteroids in our in the asteroid belt, and these asteroids are rich in organics, and they contain uh, some amount of water locked in the hydrated minerals. And a small portion of the other asteroids include the M-type asteroids, which is less than 8%. Now, why do we study asteroids? So basically, the asteroids are the building blocks of the planets. So अगर अगर हम लोग एक एग्जांपल लें कि बहुत बहुत सारे एस्ट्रॉइड्स है और these are actually the building blocks. That means these are the pristine samples from which our solar system was formed. So अगर हम एस्ट्रॉइड्स को स्टडी करते हैं तो हम लोग formation and early evolution of solar system, we can study the formation and early evolution of the solar system. Another one is, as you all know, there is a hypothesis that how the life on Earth came into existence, हमारी पृथ्वी पे जीवन का उद्भव कैसे हुआ. तो उनमें से एक थियरी ऐसी है कि एस्टेरॉइड्स या तो कॉमेट्स ने हमारी पृथ्वी पे सीड मतलब के लाइफ मतलब जो लाइफ के इंग्रेडिएंट्स है वो they are delivered to earth on earth by these asteroids. So if we study about and we have the clues that these asteroids are carbonaceous, the carbonaceous type asteroids, they have the different types of carbonaceous materials like amino acids. These are the seeds for the life. So if we study these carbonaceous type asteroids, we can study more about the formation or the origin of life on earth. Another one, as we all know that asteroid belt is a very dynamic belt. That means due to the gravitational forces and due to the impacts of different solar system bodies and comets and other stuff, it is very dynamic. That means there is always the accretion, coalescence, and other forming processes which are going on in the asteroid belt. So if we study the asteroids and asteroid belt, we can study more about these different processes which are very important to know more about the planet formation in our solar system as well as the other solar systems. And the also the other aspect of studying the asteroids is if we study the composition, that means the chemical composition or elemental composition, that means what are the things from which the asteroids are made of, like iron nickel alloys and metallic iron or silicates and other stuff. So if we know about the composition, it gives us the opportunity about the like for example अभी अभी जो अभी जो स्पेस मतलब जो स्पेस साइंस जो जिस तरीके से आगे बढ़ रहा है, तो we can it will be possible in within 20 to 50, 30 to 50 years that we will be going to the asteroid and dig up the asteroid for different precious metals and all. So it will give us the potential opportunity to get precious metals, as well as it can also prepare us for the dangers. Like for example, after some years, we can precisely calculate the orbits and how it is means कितनी दूरी से एस्ट्रॉइड जो है. तो अगर हम लोग कंपोजिशन के बारे में जाने तो हम लोग प्रिपेयर रह सकते हैं कि उसके मतलब अगर एस्ट्रॉइड आता है और हमारी पृथ्वी से कोलाइड कर सकता है, then we can think of different kind of missions where we can go in the space and blast the asteroid with the help of some nuclear bombs or something like that. It's actually the different kind of thinking which involves many stuff. But like अगर आप लोगों ने Armageddon movie देखी है, then you'll be able to know Armageddon is a movie where they are going to the, which is a science fiction movie of course, but they are going to the asteroid and dig up the asteroid and then blast it with the nuclear bomb so that it cannot collide with the earth. So these are the things that are going to happen in the future, and we need to prepare for that. So these are the things that we are going to study with the help of the asteroids. Now coming to the different missions to the asteroid belt. So National Aeronautics and Space Administration, as you all know, NASA, and also the Japanese Aeronautics and Space Administration and European Space Agency. These are the different space agencies. They have different missions to the asteroids in the asteroid belt. Like for example, I have summarized a few of the missions, like the Deep Space One from the NASA was the first space probe which fly by the asteroid. which was also the technological demonstration. And then we had the another Procyon mission from Japanese Aerospace Agency, and then we had the Rosetta, which was also the orbiter and lander later on, which was the European Space Agency mission. And we also had the mission from NASA called Dawn, which is the orbiter to the two different or bigger asteroids like Sirius and Vesta in the asteroid belt. We also have the sample return missions like such as Hayabusa and Hayabusa 2 from Japanese Space Agency, and then we also have the OSIRIS-REx from NASA. These two missions are still going on, and they are visiting two different asteroids, and they are going to dig up the surface of the asteroid and take us the sample, which is the samples will be receiving the samples in later in 2020 or something like that. So these are the different missions to the asteroids to know more about these asteroids, the composition, the surface, the morphology, and many stuff, and what are the dynamics of the asteroid belt and things like that. So I'll now discuss some of the scientific outcomes of these various missions. So discussing the first mission, which is the Dawn mission by NASA, where the Dawn spacecraft visited Vesta and Sirius, which are the two the bigger asteroids in the asteroid belt. Now it has mapped the craters on the Vesta, and they have found that there are the larger impacts on the surface than predicted by the models. So the one community which is known as the computational astrophysics physicists, they are doing models of the different solar system processes, different nucleosynthetic models, and it is a whole different branch of science. So they have made the models which can predict the impacts on the craters. But when we go and actually see when this spacecraft went on the asteroid and actually see the craters were bigger than the predictions. So what we know from that, or what can we conclude from that, that the planetesimals that are going around the asteroids or the in the solar system were larger than larger than predicted. Going to the different another asteroid was also visited by this spacecraft, which was Sirius, and it has mapped the surface chemical composition of the surface, and it has found that they have found that different carbonaceous or different molecules like ammonia, for example ammonia, and ammonia is condensed in the colder environment. So what is the interpretation? So the interpretation from this data is that Sirius was formed beyond the orbit of Jupiter because it needs colder environments to condense the ammonia. That means the Sirius was formed beyond the orbit of Jupiter, and then it was migrated inwards. And right now it is orbiting in the orbit in the asteroid belt, which is between the Mars and Jupiter. And the spacecraft also mapped the water ice or search for the water ice, and it has found that it might have the salty liquid water beneath the surface as a remnant of the ocean. That means that if we study in detail, we can learn more about the environmental conditions in the different places other than our Earth. That means we can learn more about the ocean worlds in other solar system bodies. And why it is important? Because as we know that the life was first originated in the oceans. So it is very important to know and to learn more about these kind of asteroids. Um, Now I'll be discussing about the sample return missions. There are three different sample return missions that I am going to discuss in briefly. So the first sample return mission was Hayabusa, which was planned by the Japanese Aerospace Agency, and it um, it visited the asteroid Itokawa. The name of the asteroid is Itokawa, and it also landed on the Itokawa asteroid and collected the dust particles. However, the quantity of the dust particle was very, very low, but we have many precious or many important informations which we can learn from these particles, because these asteroids are very, very primitive solar system materials, and it can give us many different kind of information. So this Hayabusa spacecraft went on the Itokawa asteroid, landed on it, collected the dust particles, and came back on Earth. So and then these dust particles were analyzed in the laboratory in a different part of world, and we have different data set. So the thermometry data, or the thermal profile of these particles, they have, and they suggest that Itokawa asteroid is a very small part of a giant or the larger parent body, which was after its formation, it was desegregated into different smaller pieces by different impacts of other kind of bodies in the early solar system. So this Itokawa asteroid is a small body, but the parent body of this asteroid was very, very bigger than as compared to this Itokawa. And the mineralogy and chemical composition and petrology, morphology, and different kind of analysis in the lab of these dust particles, which were collected from the Itokawa asteroid by this Hayabusa spacecraft, it suggests a direct link between these kind of asteroids. So Itokawa is a S type of asteroid, which we have discussed earlier. It is a stony kind of asteroid, and so they have found a direct link. So this is the first time they have found a direct link between a specific type of asteroid and a specific type of meteorites. I'm going to discuss these different kind of meteorites later in my talk, but this is the first time. So the meteorites which are the asteroid, but we have found them on Earth, and so we have the sample of meteorites on Earth, which is also the asteroid, the piece of asteroid, but we cannot say that this particular meteorite is coming from this particular asteroid. But now we are sure by comparing the two different so the one is the asteroid and one is the meteorite. So comparing the mineralogy and chemistry and different stuff, we can say that these two are directly linked. So this is very, very important discovery. So another two different missions that I'm going to briefly talk, that one is the Hayabusa 2, which is a continuation of the Hayabusa first spacecraft from the Japanese Aerospace Agency. It is going to collect the samples from Ryugu asteroid. So I guess it has already collected some part of the sample from Ryugu asteroid, and they already have the sample, but now it is on its way back to Earth. So what are the different objectives of this mission? So they are going to study the mineralogy and the volatiles, different volatiles and organic materials, which are the examination of organic materials which are planned from the collected samples from Hayabusa, which is coming back on Earth in later this year. And it is also going to study the different kind of patterns in the grain. It will give us the clue about the different physical and physiochemical environments the Ryugu may have experienced over time. So after the formation of the Ryugu asteroid, it has been it has been experiencing different kind of environments, like different impacts from the different solar system bodies, and the high energy particles, radiation from the sun, and many different things. So what are the different environments that it might have experienced, that we are going to study in this for using these samples collected from Hayabusa, collected using the Hayabusa 2 spacecraft from the Ryugu asteroid. And the another one, sample return mission, which is also currently going on, and it is also going to collect and giving us, it will give us the samples from the Bennu asteroid, which is a C type or carbonaceous type asteroid. It is also very important, very important kind of asteroid. And it will the main objectives of studying this asteroid is, so they are going to study the organic compounds. So this is a C type asteroids. It is they are going to find many different type of carbonaceous compounds, like organic compounds. And why we are studying the organic compounds? Because organic compounds are the seed, or they are the seed particles or seed to the which can give us clues about the origin of life on the earth. I have in the previous slide I have told you that, so there is one theory that the life on earth is not originated on earth, but it has come from outer space, or at least the organic compounds from which the life, like amino acids, from which the life is originated, it is delivered to earth by these kind of asteroids. So the studying these will have a very large impact as a whole on the science as a whole. So these are the different kind of sample return missions. And we'll be now switching. So we have this we have discussed the asteroids, different asteroids and different missions to the asteroids and asteroid belt. Now we are going to discuss the Kuiper belt. So Kuiper belt, as we have discussed in my first or second slide, that Kuiper belt is also another kind of belt, but it comprises of many different icy bodies. Like it is very far from the solar system. From the sun, not from the solar system. It is a part of the solar system, but it is very far from the sun. And as you go further from the sun, it is beyond the orbit of Neptune. So as we know that Neptune is the last planet in our solar system, and this Kuiper belt, the orbit of Kuiper belt is starting from the later from the Neptune orbit, like 30 astronomical units from the sun, and it extends up to 50 60 astronomical units. So this is also so like asteroid belts, these are also the icy bodies and volatiles, different kind of rocks, you can say, but the pieces of rocks but made of ice, and like volatiles and methane and different kind of stuff. And they are also orbiting around the sun, but further from the sun. And so these are in the right hand side, you can see some of the largest known Kuiper belt objects, like Pluto and Charon, which is a Pluto-Charon binary system, which is also a Kuiper belt object, but the story is a little bit different. There is a Sedna and Makemake and many different objects which are the Kuiper belt objects. And why do we want to study the Kuiper belt? Because these Kuiper belt objects are very pristine kind of samples. So, and basically it is known as the very primitive or primordial samples, which are the leftover from when the solar system was formed. So all the material of majority of the material is the sun. So like more than 99% of the mass of the solar system is the sun's mass or solar mass, and the different planets. So what are the leftover material? It is orbiting around the sun in this Kuiper belt. and these are the very, very primitive materials. So if we study, what does the primitive material means? They are not altered from the beginning of the solar system. So if we study this, we can study many things about the formation and early history of the evolution of our solar system. So I'll be discussing about the one mission, which is the Rosetta spacecraft. As I discussed earlier in my earlier slide, this Rosetta spacecraft has visited the comet 67P, which was the orbiter and lander, which is a European Space Agency mission. And when it was orbiting around the comet. Yes, one thing I wanted to tell you is that the Kuiper belt is also one of the source of the comets in the inner part of our solar system. So whatever comets, like you may have heard about Halley's comet, which is visiting our solar system every 72 to 75 years. I forgot the exact figure. So like these comets are frequently visiting our solar system, and they are coming from this Kuiper belt or the Oort cloud. I'm not going to discuss the Oort cloud, but they are coming from the Kuiper belt. And these comets are also very pristine material, but they are frequently visiting our solar system due to the gravitational forces and attraction due to the gravitational forces and different kind of stuff. So this Rosetta spacecraft, it orbited the comet 67P, which is the picture or the cartoon you can see here. This is a spacecraft, and this is a comet which it visited. And from the surface data or the surface morphology, it has two distinct lobes, or it is made of two distinct parts. This comet is a very interesting, which is made of two distinct parts. And from the data we can or the scientists can suggest that when it began as a whole body, it was these two parts were independent, and before the billions of years it collided. They are collided together to form the comet which we see today. And also there are different kind of discoveries this Rosetta spacecraft has done. Like for example, comet, it has water ice, but the deuterium or the amount of deuterium is very, very it is very, very higher amount of deuterium than the Earth's ocean. And there is one hypothesis that the water on Earth, whatever amount of water on Earth, which is currently on Earth, it is delivered by comets. But from the data of this Rosetta mission, we can rule out this hypothesis that the water on Earth is delivered by comets, because the amount of deuterium from the comet and the Earth's ocean water is very, very different. So the water from water has not come from the comets, which is basically पानी जो है पृथ्वी पर वो comets से नहीं आया है. Comets has not delivered the water. And another discovery, which is the organic compounds. It has organic compounds, and studying these organic compounds, we can say, like as I discussed before, we can discuss about, or we can know more about the different we can know about how the life was originated on Earth, or what are the different ingredients which may have delivered to Earth by these comets. And this comet specifically, this comet has this kind of organics. So this is also a very, very important discovery from this Rosetta mission. And I'll discuss another mission briefly, which is a New Horizons mission, which was planned to visit the Pluto and Charon, which is a binary system in the Kuiper belt. But after visiting the Pluto Charon system and giving us many data in 2015, it also encountered a very pristine solar system sample, which is known as Arakoth 486958, which is a number, and Arakoth, which is also a very pristine solar system sample. So like I told you earlier, so by studying this sample, we can tell us more about the formation and early evolution of our solar system. So it has like a snowman like structure. So if you see here, it looks like a snowman. So if you have visited some snowy places in India or abroad, you may have made this snowman like structure. So the structure is like a snowman. And so it also has two different lobes. And from all the different kind of data which this spacecraft, New Horizons spacecraft, has found, the scientist can confirm that there is a theory which is called the Pebble accretion and the planet formation process. So all the kind of data are matching with the model, which is a Pebble accretion. So there are the small pebbles which come together not by gravitational forces but by the streaming instability, which is a physics term which I'm not going to explain in detail. But due to the gas drag, these small pebbles or particles came together to form a pebbles, and then they have made a cloud which collapsed to form different kind of planetesimals, which are which grew together to form gas giants or the planets like Jupiter and Saturn and Uranus and Neptune. So you see, so using this data or using this different kind of missions or the data from the missions, we can tell us more about how the gas giants or the planets may have formed in our solar system. And it is very important to know, because now we are also studying the exoplanets. So the planets which are forming right now in the other solar system or the solar system in the other worlds. So the how the planets are formed, we can study more in details using the data from such kind of missions. So these have a lot many impact on the current science or the science of understanding the formation and early evolution of our solar system, planets and stuff like that. So with this, I'll now switch. So I have discussed from my side. I have discussed two different belts. So asteroids in the asteroid belt, and comets and the missions to the comets, and the different kind of missions that we have from NASA and other space agencies, and the Kuiper belt objects, and how the data from different missions have impact on the science of the solar system. Now I'm going to discuss a little about the meteorites. So as we know that the meteorites are real, of course this is a cartoon. The meteorite is coming towards the earth, and due to the drag and the friction, it is looking like this. And but we have different craters on the earth. Like for example, I have taken the example of the meteorite crater in Arizona. So when meteorites are coming towards the earth, they collide to the earth's surface and impact and made a crater kind of thing, which is the here you can see here. And so now, so we have the pieces of asteroids that we are so the meteorites are nothing but the pieces, the small pieces or of rocks, or the part of the asteroids that come on the earth, and we can collect them. We can collect them from different places. Like this is a desert, Sahara desert. This is the Antarctica. There are different parts of earth where we can easily find the meteorites. So there are different dedicated missions The people are working for collecting the meteorites. So different parts of the world, universities and institutes, they have the large collection of meteorites. And so these are the pristine extraterrestrial samples that we have on Earth, and we can, by studying them in laboratory, we can tell us. So these nature has given us. So one, we can go in different missions, we can go on asteroids, we can go on comets and collect the samples. And another thing, the nature has provided us with the samples which are coming towards Earth, and we can collect them and analyze them. So why do we study meteorites? So as I have discussed in my earlier slides, that different elemental and isotopic composition of these meteorites, which are the building blocks of the planets, and we can study more about the early evolution of our solar system. And some of the meteorites contain very pristine calcium aluminum rich inclusions and chondrules, which are the first forming solids in our solar system. And by different lab methods, analysis methods, we can tell us the chronology of or the age of our solar system, which is 4.5, approximately 4.5 billion years. It is possible due to the samples which we have, the meteorite samples which we have on Earth. And using the thermal profiles or the temperature profiles, we can tell us more about how these asteroids and what are the different conditions the asteroids might have experienced in the outer space or extraterrestrial space. And the shock and impact histories can also give us about the impacts. And some of the primitive meteorites like Murchison meteorite, it also contains the organic materials, which are like, for example, amino acids, which are the building blocks of life on Earth. And we have discussed earlier that this might have originated or started the life on Earth. So studying these meteorites, these kind of meteorites and primitive materials, which has a large impact on the community or scientific community as a whole. So this is the general overview of the early solar system history. So this we have, I will quickly go through this slide. So there we have the formation of calcium aluminum inclusions, which are the first forming solids in our solar system. And this is the protoplanetary disk. I'm not going to discuss in more details, but the calcium aluminum inclusions and chondrules are the first forming solids. And analyzing them, they which we find from meteorites, CAIs and chondrules, and analyzing them in a laboratory, we can tell us exactly when our solar system was formed. So the number is 4567 million years, or 4.567 billion years. This is only one example, so that what we can learn from meteorites. These are the different kind of meteorites, different types of meteorites, having different. So this the white thing you can see, these are chondrules and calcium aluminum inclusions. You can directly see here, and these are different kind of meteorites. I'm not going through the classification of meteorites. There are mainly two different kind of meteorites: the differentiated and undifferentiated ones. The differentiated meteorites are primitive bodies, and undifferentiated are the primitive bodies. And differentiated meteorites are the melted in different solar system events by impacts and due to the heat and other stuff. And these kind of meteorites give us different kind of details. I'm not going into details. I'll discuss briefly about what we are doing in laboratory. So these different meteorites contain a very small amount of particles, which are less than 1 micron. And these particles have originated in the stars before the solar system formation. So we know that there are different kind of stars, and they have incorporated material in the molecular cloud from which our solar system was formed. And using this by studying these particles which are found in meteorite samples, we can tell us more about the stellar nucleosynthesis, how how the stars are born and what are the different elements created in stars, and we can study more about the how the meteorites may have altered and different kind of physical and chemical environments in the stellar environments like AGB stars and supernova and stuff like that. This is the research. This is my research field. I have studied more about the stardust grains in my PhD during my PhD. This is the NanoSense, which is a dedicated instrument. This is only only one kind of instrument in India, which is in the PRL, Physical Research Laboratory in India, and I have worked on this machine, and along with Lalit. Lalit also has worked on this machine, and we had a long story of working with different kind of samples. And this is a secondary ion mass spectrometer, which is a very highly sensitive instrument dedicated to work on these kind of samples, meteorite samples. And this is only a little bit a part of example of my thesis, which these are very small or small meteorites, the pre-solar grains, which I have studied in my PhD. And you can see here that the hot spot which we have analyzed, these are coming from AGB stars before the formation and supernova before the formation of our solar system. So by studying these stuff, we can study more about these kind of stars and how these stars may have incorporated material for the formation of our own solar system. With this, I will conclude my session. I apologize, Lalit, if I have done a bit more in my lecture, and over to you, Lalit.
Thank you so much. It was such a nice presentation, and you explained a lot of things. So, as of now, after the lecture, I promised we are going for a question answer session. So, there are few questions from audiences. So, we will be talking about that. We're taking the questions and discussing how we can get to them and get them answer for what they're looking. So
sure.
There is one question by. I'm looking at that question. Yeah, this question by Vishwajit Maurya. He's asking. Probably he wants to know that how we name these solar system objects. So the kind of meteorites and asteroids. So it would be great if you put some light on how we name that.
Okay, so I'll take one example. So these meteorites that we are talking about, these are the pristine samples which we collect from the Earth. So from the places on Earth from which we collect these samples, these meteorites are named accordingly. For example, there is a meteorite which I analyzed, which is called Ishievo. So Ishievo is a part of Russia. So you know the country Russia. So Ishievo is a part from which this meteorite was collected. So it was given this name Ishievo because it was collected from this part of the world, or this part of the Earth. For example, another example I'll be giving. It is a Northwest Africa meteorite which I studied in my during my PhD, which is NWA 801. The name of the meteorite is NWA 801. Why it is called like this? So because NWA is the Northwest Africa. So it is the region NWA, Northwest Africa, from which this meteorite was collected or this meteorite was sampled. So according to the place from which we collect the samples, we are giving the names to these kind of meteorites.
Yeah, thank you so much for. I think he got the answer. And another question from Yuval Makwana. He's asking, what will happen if meteorite fell in Antarctica? This is a very interesting question. If meteorite meteorite can fall anywhere. So what will
Yes.
happen if meteorite fell in Antarctica? So it is something good,
Yes.
I think. So
Right. Yeah.
please, you take this question.
Right. So why we are looking into Antarctica? Because Antarctica is a like a very very deserted area in the form that, so like it is very cold and it is isolated from many kind of human activities. So meteorite can fall in any part of the earth. But why we are looking into the Antarctica? Because it is very very easy to find the meteorites on the vast icy background. So in Antarctica we have snow and ice everywhere. So if the meteorite has fallen on on the ice, so so meteorite is basically black because of
Yeah,
the friction. So while it is on the ice, it is very easy to very easy to find them on the ice. So that's why we are looking into Antarctica. And another one, so Antarctica is it is a very less chances that the meteorites are altered in the
yeah,
Antarctica, because while it is buried in the Antarctic ice, it can be prevented for many thousands of years. So that's why
yeah.
it is
Basically,
important to look for.
yeah, you mean to say that if meteorite falls in Antarctica, that's a good
Yeah.
thing, and it remains pristine and preserved for a long
Yes.
time, and we
Yes.
go and search for it,
I,
and
Yes, I'll add to that. So there are different universities and institutes. They have dedicated missions. So one I know is ANSMET, so Antarctic Search for Meteorites. So they train people to go to Antarctica and be there for like 15-20 days, and then collect the samples for us, and then we can use them. Yeah. So
yeah,
so
actually, in continuation, I would like to put one more question. Okay, how to identify? Just meteorites, you told the meteorites are like rocks. So how to
yeah.
identify this rock? If I get a rock to you and say whether it is meteorite or not. So
Yes.
since you have worked on that very field, so you will be able to tell some very initial things by which we can look at the rock and say it is a meteorite or not.
Yes, definitely. So the basic thing or the main thing which we are looking to differentiate between the normal rock and meteorite. So it has this very thin fusion crust. So what is that? So when the asteroid or the rock is coming into the Earth's gravitational field, there is a lot of friction, and due to the friction, it has been heated to very high degrees, and that's why
Yeah,
the outer surface of the piece of the rock has been melted and then has been coolened, so that there is a how to say, there is a very thin amount of layer
yeah,
on this rock. So it is not usual to other kind of rocks on Earth. So so
yeah,
if
yeah.
you
It is
yeah,
it is the first
yeah,
thing to look when you get a rock and somebody says it's meteorite. So it is the first thing
yeah,
whether
yeah,
its crust is burned in the Earth's atmosphere while it entered there.
yes,
Okay, thank you
yes,
so much. And, there is a few more questions. Let us take on that. One
yeah,
question by Vikram Goel. Vikram Goel is asking,
yes,
is asking, there are many possibilities of evolution of life on Earth. What is your opinion about evolution of life on Earth? So you have almost discussed this thing, okay, how life
yes,
evolved when there is a possibility that when some asteroid hit and gave some elements, some material to start in life. So probably
yes.
we want to more about that. So you can take a little bit.
Okay. Uh, I think I'm not in a position to to answer this in a in a confirmed way, but
Yeah, it is not some one-liner question. But it is like
yeah,
you have
yeah,
discussed a little bit about different possible theories, and
yes,
there. So there is a theory that some asteroid hits Earth and it delivered some material
yes,
it was necessary to start a life
yes.
on Earth.
Yeah, so I believe that, I mean, so it might be it might happen that these so they have so these asteroids and comet impacts, this might have created some kind of environment which 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 can easily how to say, which can easily start the life on Earth. It may happen that these kind of impacts have created some environment in the early Earth, or the early times of Earth, so that the life can be easily started on Earth.
Yeah. Okay. One more question from Vagish Mishra. He is asking how similar is the composition of stony meteorites with us. So, is there any similarity with this stony meteorites?
Okay. I'm not totally sure about this, but
I think he means to know. He means to know about the composition. Means when we are talking about composition, so there are two things. One thing is that we talk about elemental composition. One thing we call about isotopic composition. So
yes.
it is basically he needs to know why. What is the difference between this? Probably he wants to know about the isotopic composition, difference
So
of
I
Earth composition.
Yes, I guess using the oxygen isotopes. So
Yeah.
I also have studied the oxygen isotopes in my meteorites, but in a different scale. I have studied very small particles in the meteorites. But using the different using the oxygen isotopic compositions, we can differentiate between the stones on Earth and the stony meteorites.
Okay.
So if
So yeah, I think it takes to this question. So so it is really a good session, and we had a lot of questions. So we took some question as per time available to us, and
yeah.
so so one question is by this Vikal Makwana. He asked before that what will happen if a meteorite falls in
Yeah.
Antarctica. He's asking me for any example. So for an example, actually we can talk about. You told the detail that there are very specialized missions on
Yeah.
when people go and collect.
Yeah.
So you can little bit talk
Yeah.
about that missions and how they name it or like.
Yeah, I guess there are different places in Antarctica. From so I explained it earlier that there are different. I can recall two names. One is the Ellen Hills, and another is GRE or something like that. I forgot the name. But the Ellen Hills meteorite is a very famous Antarctic meteorite. I forgot the. I can't recall the number that they have given, but the Ellen Hills meteorite is coming from Antarctica. You can search on the internet, and you can find it. And one is, I
Okay.
guess, QE, Queen Elizabeth, something like that. I can't recall the exact name, but yeah, these are the different parts in Antarctica from which these meteorites are sampled or found.
Okay. So we take one last question.
Yeah.
Shraddha is asking कि meteorite maximum कितना बड़ा हो सकता है? So
Wow.
can you take this? कितना बड़ा हो सकता है
Uh,
maximum?
right. I'm not sure about it, but it can be like some hundreds of meters that we can find on Earth, because if it's very big, then it can shatter the Earth, but it can be some meters big
Yeah,
when
it
when
can
it
be.
when it reaches, yeah, when it reaches the Earth.
Yeah. And Vikram Goyal has something to say that this is the name of meteorite. It is a Martian meteorite. This was found
Okay.
in Antarctica. So this kind of names
Ellen,
was
yes,
given. Yeah.
yeah. Right, but and it is interesting. Yes, thank you, Vikram, for this information. So it is coming from Antarctica, but it is actually a Martian meteorite. So when people has analyzed it and so like elemental and isotopic composition, it is similar to the Martian rocks. So it is very interesting that this is a Martian meteorite, but it has found from Antarctica.
Yeah, so we had a very nice question and answer session, and it seems that is the objective, to get into the details, and we had a very good interactive session in the lecture. So, uh, so Professor Chichester is was with us now, and but for some time he's having some network issue probably, so he's not with us. So I'm waiting for some more time so that he can join, and then we will proceed further. So for as of now, we have one thing. Ritesh sir is telling one more name for the meteorite in Antarctica. This is uh, so this is really good that we have all our people with us, and we are having a very good interactive session. So this is really uh, so one thing, just for 1 minute, I have a very popular kind of thing, a very popular question. That many times we see that there are 9 planets in our solar system. Okay, so
Yeah.
and then it comes that there are 8 planets in solar system. The Pluto is there. Sometimes it becomes planet. Sometimes it becomes it is not a planet. So what is the reason? What makes it what makes to qualify it as a planet, and why Pluto is not a planet? Can you talk a little bit about that?
Um, uh, so I guess the main thing, if you see the orbit of Pluto, it is very inclined as so yeah. So there are the international organizations has certain definitions for which if a rock or a body, certain body is fulfilling these definitions, it can, we can say that it is a planet. So according to the Pluto, one thing is I guess the orbit, which is very inclined as compared to the so like this is the plane of the solar system, and the orbit of Pluto is like inclined orbit, which cannot be the case for becoming it as a planet. And another thing, I guess, is it is a Pluto, and it is not alone, which is a binary system. Pluto and Charon is a binary system, and the another body, which is a Charon, it has the mass which is higher as compared to the Pluto. So it cannot be the case for the for the Pluto, which can be certified as a planet. So as far as I know, these are the two reasons. There can be another reasons, so that why the Pluto has misfortune to not becoming as a planet right now.
Yeah, so that is very interesting information. I think all the young students who have joined us,
Yeah.
and all science institutes, we have really enjoyed this session, and I'm
Yes.
really happy that we conducted this session, and very important information, very important frontiers of research, and very questions for common people who think about solar system, and these asteroid belts and Kuiper belts, and how these belts provide a lot of material. I mean, so these meteorites and comets, these samples, when we get it in the Earth delivered, means this is an opportunity to
Yes.
have samples from such a pristine, containing such a pristine information about solar system and its formation. So it was a wonderful discussion, and that is uh, uh, still we have some issue with Professor Dixit sir. He is not able to connect with us. Probably there is some network problem. So as of now, what we can do, we can proceed, and we will continue waiting for him. Whenever he joins us, we will ask him for the concluding remark for our session. He probably listened that, but he was busy initially with something, and later on there is some network problem. He is not able to connect with us. So what I can do is, before closing this segment after today's session, I will be talking about what we have in plan for next Friday. So this is very important and very interesting series. I'm sure that you all who have joined us and later on will be listening this lecture series really enjoy and enrich themselves to understand and have a better understanding and exploration of our solar system. So I would love to invite you all who have joined us now and those who will listen us later for the next session of this series next week on the same day, at the same time, and at the same platform. Up to now, we have been talking about our solar system. So first day we talked about formation. In inaugural session, we had very interactive, very good discussion about solar system evolution and formation of solar system, and a lot of other things. We had in one lecture where we hosted Dr. Vagesh Mishra from Max Planck Institute for Solar System Research in Germany. So he told a lot of information, a lot of things currently being done in the solar system research, in the solar research. Means he was talking about the startup of our solar system sun. And today we discussed about different belts, asteroid belts and Kuiper belt. So these belts we discussed, and meteorites, comets, and different missions. So now we are moving. Next week we will talk about whether there are any other solar systems, whether are we unique, or we have something to look around for something similar in our galaxy. So for that very discussion, we have a very special guest with us next week, and so we will be talking about whether our solar system is unique. What do we know? What do we know about other solar systems? क्या और सोलर सिस्टम भी ऐसे एग्जिस्ट करते हैं? क्या हम लोग का सोलर सिस्टम एकदम सबसे अलग है? ये सब चीजों को हम लोग समझने का कोशिश करेंगे. What do we know about other solar systems? And उनको कैसे सर्च करते हैं? How do we search for them? How do we know that there are other solar systems? उनको कैसे समझते हैं? उसको समझने के लिए to go into that greater detail, we will have very special guest with us, Dr. Priyanka Chaturvedi. She will be with us to talk about that very topic I have discussed. So she is currently working as a postdoctoral fellow at Schwarzschild Observatory, Thuringen, Landesstelle Kautenberg in Germany. So probably I tried to pronounce it properly, but it's a German word, so maybe it's not a correct pronunciation, but I have written it on the screen so you can look at it. It is a very special observatory for such kind of work, and it is going to be one of the best sessions of the series, so don't miss it. And thank you so much for joining today and being part of this series. Your connection to your presence is the reason we will be able to do a lot of future talks in this series, and we can plan. We are working on some very other important topics on which we can do something. So thank you so much, Dr. Manish Sanghani, for being with us and delivering such a wonderful talk. And it seems that Dikshit is not able to join us today. So he is the chairman for this lecture series, and I have his continuous support and guidance being a source of inspiration for all of us. So although he is not present, but his support and his mentorship is the force. So I would like to thank him and express my sincere gratitude to Professor Dimbi for chairing this lecture series. And I'm sure that we will be having him next week for the full session, and his continuous support and mentorship will continue to inspire us and all young students to dream for a better world. Thank you for joining this session. With that remark and the invitation for the next upcoming lecture, I thank everybody for joining us and invite you for the next upcoming lecture. So with that, we are closing session for today. We are signing up. Thank you so much for being here, and we will be meeting next week at the same time. Thank you. Thank you again.